Black holes, they're basically the universe's ultimate mystery boxes. These are regions of spacetime so extreme, they literally break the known laws of physics. We can't see inside them, we can't get any information out of them, but today, we're gonna do the impossible. We are going on a one-way trip. So let's really get into it. Forget all the science fiction for a minute. What does real physics say would happen to you on this incredible journey? We're gonna explore every single step from the safe distance of your screen, of course. All right, before we take the plunge, we have to understand the force that's in charge of everything here, gravity. But it's probably not what you think it is. You know, for centuries, we all thought of gravity the way Newton did. Just a simple force, pulling things together, like some invisible rope connecting an apple to the earth. But then Einstein came along and just completely rewrote the rulebook. He said that massive objects don't pull on things. They actually warp and bend the very fabric of space and time around them. Imagine you put a heavy bowling ball on a trampoline. It creates a big old curve, right? Well, if you roll a marble nearby, it's not being pulled by the bowling ball. It's just following the curve that the ball created. That is Einstein's gravity. And a black hole? It's like an infinitely heavy bowling ball. So to really get a grip on this gravitational trap, we need to talk about something called escape velocity. Here on Earth, if you want to launch a rocket into space so it never falls back down, you've got to get it moving at about 7 miles per second. That's our escape velocity. Every single planet, every star has one. And the more massive and dense the object, well, the higher its escape velocity. And this right here is the whole deal with a black hole. Its gravity is so mind-bendingly intense, its curve in spacetime is so steep that its escape velocity is faster than the speed of light. And since we know that nothing in the universe can travel faster than light, that means exactly what it says. Nothing can escape, not even light itself. It's the ultimate cosmic trap. Okay, let's fire up the engines on our hypothetical spaceship. As we start getting closer, we're going to find out that the danger doesn't just start at the black hole. The entire neighborhood is a total cosmic nightmare. Long before you even reach the point of no return, you'd run into the accretion disk. Now, this thing is a swirling vortex of gas, dust, and shredded stars all spiraling towards their doom. The friction in here is so unbelievably intense that this stuff heats up to millions of degrees, blasting out these deadly high-energy X-rays. You've also crossed something called the innermost stable circular orbit, or ISCO. That basically means a safe, stable orbit, not possible anymore. From here on out, you're on an unavoidable inward spiral. So let's say you've somehow survived all that chaos outside. Now you're approaching the most famous part of a black hole, the boundary that has captured our imaginations for decades. This is the event horizon. Now, it's not a physical surface you could crash into. Think of it more as a mathematical line in spacetime, the line where the escape velocity finally becomes equal to the speed of light. It's the ultimate prison wall. You can get in, but you can never, ever get out. No information, no light, nothing escapes from beyond this point, ever. Okay, but this is where your brain is going to start to hurt a little, and it's all thanks to Einstein's relativity. See, your experience and the experience of a friend watching you from a safe distance are completely different. Your friend would actually see your spaceship slow down as it got closer and closer to the event horizon. The light from your ship would get stretched out by gravity, shifting toward the red end of the spectrum. That's called gravitational redshift. You'd appear redder and dimmer and slower until you seem to just freeze in time, right at the edge, and eventually fade away completely. From their point of view, you never actually cross. But for you, it's just another moment in space. You'd sail right across the event horizon, totally oblivious to the fact that you just passed the point of no return. You've crossed the boundary. There's no turning back now. What happens next is probably the most famous and, let's be honest, the most gruesome part of this whole journey. It all comes down to a really simple fact. Gravity gets stronger the closer you are to something. Well, near a black hole, that change is incredibly steep. So if you're falling feet first, the gravity pulling on your feet is way, way stronger than the gravity pulling on your head. This huge difference in force would start to stretch you, pulling you longer and longer while squeezing you thinner and thinner, kind of like a piece of spaghetti. It's a process physicists maybe a little too cheerfully call spaghettification. Eventually, you'd just be torn apart into a thin stream of atoms. But wait, here's a crazy twist. Whether you get turned into spaghetti before or after you cross the event horizon actually depends on how big the black hole is. For a small stellar mass black hole, those tidal forces are extreme even outside the horizon. But for a supermassive black hole, we're talking millions of times the mass of our sun, the gravity at the event horizon is much gentler. You could actually cross it completely unharmed, and the fatal stretching would only happen much, much deeper inside. Wild, right? So, after that incredibly chaotic journey, you might think black holes are these infinitely complex things. But the reality is, it's the exact opposite. In physics, they are shockingly simple. Yeah, this is a famous quote from the physicist John Archibald Wheeler, and it sums up this really powerful idea called the No-Hair Theorem. It doesn't mean they're literally bald, of course. In this case, hair is a metaphor for all the complicated details of whatever fell in, whether it was a giant star, a planet made of ice, or an antimatter spaceship. Once a black hole forms and settles down, all of that extra information is basically lost to the outside universe forever. All that's left are three, and only three, properties that you can see from the outside. You can describe any black hole in the entire universe just by knowing its mass, how fast it's spinning, and its electric charge. That's it. Every other detail, just wiped clean. So those three properties give us a few different types of black holes. The simplest one is the Schwarzschild black hole. It's just mass, no spin, no charge. But in the real universe, stars spin. So when they collapse, that spin sticks around. And any electric charge would pretty quickly attract opposite charges and neutralize itself. So the model that actually describes the black holes we really see out there is the Kerr black hole, one with mass and spin. This is what astronomers are actually testing when they look at these cosmic giants. Okay, so if everything that falls in just gets crushed and all its information is lost, what about that popular sci-fi idea of black holes being some kind of portal or gateway? I mean, it's a really cool thought, isn't it? The idea that you could pop into a black hole and just pop out somewhere else in the universe, or maybe even in another dimension. Is there any actual science to back that up? Well, believe it or not, the math behind Einstein's theories actually allows for this. It predicts a theoretical shortcut called a wormhole, where the entrance of a black hole could be connected to the exit of something called a white hole, creating a tunnel right through the fabric of space-time. But, and this is a big but, here's the catch. While the math works on paper, these cosmic tunnels are predicted to be unbelievably unstable. The very instant anything tried to pass through, the wormhole would collapse in on itself faster than the speed of light. So for now, science says a black hole isn't a tunnel, it's a one-way street to a dead end. Our journey into a black hole ends at the singularity, a place where our understanding of physics completely breaks down. They may not be gateways, but they are laboratories for the most extreme physics in the universe. They challenge our deepest theories about space, about time, and about information, proving that even in the absolute darkest places, there are profound secrets just waiting to be understood. What do you think we'll discover next?